And now on to the exciting world of Kalman filters. So if you remember from where we ended last, we've gone over a few times where the Kalman filter comes from, the whole prediction and estimation part of the process. And we were setting up a MATLAB example where we were going to estimate the velocity from the position. So this is just a copy and paste from what we had last time. It shows that we're going to be measuring a noisy signal from sonar that shows altitude. So the position goes from roughly 20 to 100-meter altitude and kind of oscillates and things. From that, we also wanted to get the velocity. We wrote this in a way that it's in the format of the Kalman filter. So the key things were you need to write something in this form where you got to get a matrix A that's independent of your state X, and then this measurement formula with this other matrix H that takes in the state and says what the measurement is. So the way we set this up, we said, well, the state, we're going to set up the state as it's the position and the velocity at time K. We could write that, the position and the velocity step forward using this matrix A. And down here, it sort of shows what this does. The position and the velocity at time K plus 1 is the position at time K plus the small increment in position, which is delta t, the time between measurements, times the former velocity. And then we're just saying that the velocity stays the same. For this sonar example, delta t is 0.02 seconds. So that's a parameter that goes into the A matrix. Because we're measuring only the position, H, I said, was this matrix 1, 0. And if you multiply that times the state, which is position and velocity, you do recover the position. So that was the A matrix and the H matrix. Those are two of the four matrices you have to determine for the system model. Everything else is just part of the Kalman filter algorithm, and you don't change that. So I just sort of said the noise here, at least the state noise, is 1 and 3. So 1 in the position variable, 3 in the velocity variable. R is the measurement noise, and we're assuming that's going to be a little bit larger. With this, it's pretty noisy. We'll also give it some initial state, which I don't think it really matters much here, but I'll say it's starting at a height of 0, so a position of 0, and a velocity of 20 meters per second. And I don't really know what the uncertainty is. I have pretty high uncertainty. Remember this P matrix? And this is just to initialize. After a very few time steps, the Kalman filter will kind of take over from this. We want something that's just not completely crazy. So this just means I have high uncertainty in both of those. That's all. So now we'll go to the MATLAB and see how this does. Are there questions about this? About where A came from, H, or anything? The noise I basically just made up. You could get that by tuning if you want. So trial and error. Let's go to the code. This is also in the Google Drive for this lecture. I'm doing DV Kalman. When DV Kalman, we've got this thing that just gets the sonar data. I think you remember what the sonar data was. This is test Kalman. So there's 1,500 samples in that sonar data. This first step just sort of initializes, just fills them all with zeros, and then we step through the algorithm. So we're getting the sonar, which is our position, putting it through the Kalman. When you first run, this says that the dt is 0.02. Here's the A matrix. Here's the H matrix. Q are the initial X guess and the initial P guess. And then everything below this is just the Kalman filter algorithm. Haven't really changed it. And then this spits out the position and the velocity. So if I run this, it's plotting two different things. First, it's plotting, this is something we did before where we got the position from the sonar. The red dots up here are the measurement. And in the blue curve is what the Kalman filter gives. And you see it's nicely within the middle of the measurements. The velocity that's also estimated is shown down here at matching time. So we would expect this thing is going up, so the velocity is positive, and then it's sort of hovering around 0, and then it should go down and hover around 0. And that's what we see. This says position, but this should be velocity. This is velocity starting positive, and then it sort of hovers around 0. and then it's negative, and then it goes back to 0 and without too many wiggles. So the Kalman filter is actually good for estimating velocity. What would be another way we could have estimated velocity? If you have position and you want velocity, is there anything you could do? What is it? Yes. Yeah. We could take finite differences. You could say position at time k plus 1 minus position at time k divided by dt, and that should give you velocity. And so I want to show you what that gives. Let's compare that. So if I think I need to do something like this, just getting my time axis right. Velocity estimate would be the differentiation of the actual measured thing divided by dt. So diff just means it's going to take a difference. So this would be another way to estimate the velocity. Now, if I go to figure 2, and I'll plot this in red, T vel est, make it red. Before I do that, let me do hold on. The axes change because that estimate of the velocity just by taking finite differences is so noisy and terrible. You can see within there what the Kalman filter gets is just way better, way smoother, less noisy. You wouldn't want to use finite differences. You'd actually want to use the Kalman filter because it's taking into account that there is noise in these signals. So it's giving you the best estimate, especially if you had some control system that's based on what this instantaneous velocity is. This is getting it off by orders of magnitude. So you wouldn't want to use that. Kalman filters are better than just sort of our naive differentiation. So I guess we could say we were successfully able to estimate the velocity from position. The reason we were able to do that is because we have a good model. We know how position and velocity are related by our model, basically that A matrix. And it was much less noisy than a naive approach to, maybe we'd say straightforward. I don't want to be insulting. What would our first guess be to estimating velocity? Which would be something like the velocity at time k is v or x, k plus 1 minus x k divided by delta t. That's what I did for the second one, and you saw how noisy that was. Very noisy. Because the measurements were noisy. Right, well, hold on. What if you differentiated that Kalman filter position curve? Maybe you'd get something less noisy. You still get something noisy, and it is less noisy, but it's still not as good as the full estimate. Okay, so that was for just trying to get a one-dimensional velocity from a one-dimensional position, just to demonstrate that you could do that. So you could do this, let's say you're trying to estimate the position of, or the velocity of a vehicle, and you've got both x, y, and z components of velocity. You could use the same thing. You'd have 6 states, 3 positions, and the 3 velocities. If you wanted to estimate acceleration, you get that as well. Or if you had an accelerometer, you could try to estimate velocity and position from that. That's a little bit harder, but you can go that way. I'll just sort of mention that in passing. You can estimate velocity and position from accelerometer data. Accelerometers will show up later today too. So are we ready to go to full-on attitude dynamics? Point of the class, right? Now we're entering into dynamic attitude determination, and we're going to use a lot of things that we've prepared ourselves for. Determination is maybe a little bit too grandiose. We don't know if we're doing it right. So to be humble, we might call it estimation. And we're going to use a Kalman filter eventually, but first we'll see what we could do without one. So let's say we have sensors. We've got a gyro, which is a gyroscope, and an accelerometer on a craft, whatever that is. So the gyroscope gives you angular velocity. The accelerometer gives you accelerations. And these are both in the body fixed frame. A lot of your devices have that built in as well. I've got this thing called a WIT motion I guess you would call it an IMU, inertial measurement unit. It was pretty cheap on Amazon, like 40 bucks or something. I just bought it for fun. So now it's detecting this device. We'll go to angular velocity. So this has on it what the X, Y, and Z positions are. I'm going to try to line this up the way the usual convention for an aircraft. So that means there needs to be X, Y, and then Z going down. I'll just attach it like that. If you read the right edge of that, this is showing there is no angular velocity. If I rotate in roll, so rotate about the x-axis, it's showing that angular velocity oscillating in red. If I stop and then I go in pitch, let's see, that's oscillating in green. And if I did yaw, that's oscillating in blue. All right, it doesn't know, it's showing 0 no matter what my orientation is. To get the true orientation, let's say these start out, the inertial frame, which is the red frame, if these start out aligned, that means yaw, pitch, and roll are 0, 0, 0. And so if I have some measurement of how the angular velocity is moving, I should theoretically be able to reconstruct after some time, like 15 seconds of this crazy motion, what this orientation is, either in yaw, pitch, and roll or with Quaternions or however. So we could try that, see how that goes. So what could I do if I've got the angular velocities? Let's say I don't know anything about Kalman filters. What could I do? I could integrate, yeah, like we did in earlier homework. So that's what we'll try. Let's try integration. So let's try to integrate the 3, 2, 1 yaw, pitch, and roll Euler angle kinematic differential equation, which, to refresh you. All right, so this is giving me kinematic differential equation, where this is the output that I get from the gyro of my inertial measurement unit. So the gyro gives omega 1, omega 2, omega 3. I'll write it this way. In the body fixed frame, got some B frame, and I want to know how this is changing with respect to some N frame, N, B. So this is measuring the angular velocity of the B frame with respect to the N frame. So that's really what the gyro is giving. It's giving what we've called B with respect to N. But it is writing it in the B frame because that's the only frame this thing knows about. It only knows about itself. So it knows how the angular velocity is changing with respect to its own axes. All right, but if we want to get yaw, pitch, and roll, we could integrate this ODE. These are the Euler angle rates, psi dot, theta dot, phi dot, and then you have this expression that's got the Euler angles themselves, this 3x3 matrix, times the angular velocity. So we could see how that goes. So I've done a calibration test. This is what we'll use as our input. I'm not going to use the input I just produced there. I'm going to use an input that looks like for the omega 1. It'll be some oscillations that are supposed to trigger oscillations in roll, and then I'll do about another minute of roll and then nothing. And then omega 2, I'm going to do nothing for about the first minute, and then the second time that roll is excited, I'm also going to be exciting pitch, but then I'll excite pitch again when there should be no roll. I want to know what this does. And we'll say the orientation or attitude starts out at yaw, pitch, and roll 0, 0, 0. This is all with time. Starts at t equals 0 with yaw, pitch, roll 0, 0, 0, which means the inertial frame and the body fixed frame are initially aligned. Now I can show you what the true roll and pitch are. This is the true roll and the true pitch. So this is showing that I had the roll oscillating for about a minute at plus or minus 30 degrees. And then I did it a second time, plus or minus 30 degrees. And then same for pitch for that second minute. Then for the third minute, just pitch. This is what I want to get out of the Kalman filter because this is the actual input. I mean, not the Kalman filter, any algorithm we do, and we're starting with integration. Let's try it. We'll integrate that ODE, this ODE in MATLAB. So go back to MATLAB, see what we can do. So you'll find in the Google Drive, there'll be this thing called 13.ARS. ARS stands for Attitude Reference System. I'm going to use this test Euler integrate. There are about 41,000 data points separated by 0.01 seconds. There's my initial yaw, pitch, and roll. And then I will just integrate that. And it'll plot it for me. And I want you to notice it's taking a while because it's using one of those numerical integration schemes. This is what I'm getting out for what it thinks just based on integrating. And I did the highest level of tolerance I could, meaning most accurate. It's not giving me what I expected. Forget about the yaw for the moment. In terms of just the pitch and the roll, this should be 0 and then some oscillations. It's getting some of the oscillations, like plus or minus 30 degrees. Then this should be 0, but you notice there's drift. This is drifting down. This does some weird drift. And then this thinks some additional roll oscillations happen, which didn't. Pitch is even worse because it's drifting from the very beginning. It's not staying at 0. It's doing this drift. This is just something inherent to numerical integration, especially if you're given a noisy input. This is, I think, a good gyro. There are cheaper ones that would give even more noise, but even with this one, you get this sort of drift so that some of the trends seem to be right, but this is drifting away from the truth. It's looking like numerical integration isn't working. Maybe we should try the Kalman filter, and its magical properties will save us or something. We'll see. So we got drift, and that's not very good. There was some similarity to the true signal roll and pitch, not rule, roll. There was drift, likely due to a noisy gyro input, even though by eye the noise seems small. So the errors accumulate to the point that the true yaw, pitch, and roll was just lost. So let's try a Kalman filter. We first need to come up with a system model. Now, if we use for the Kalman filter the yaw, pitch, and roll as our state, let's see what happens there. But what the state is what we call X. So if for X we've got yaw, pitch, and roll, then what? We need to write the model as the yaw, pitch, and roll at time k+1 equals some matrix A times the yaw, pitch, and roll at time k, where A has to not depend on X. So it can't depend on yaw, pitch, and roll. But if you look at what we have, we could write an ODE in terms of this form if things are right. And I don't know if they're right here. So if we wanted to, we would say, okay, X at k+1, which is yaw, pitch, and roll at k+1 equals, we probably want to write it this way, yaw, pitch, and roll at time k plus something due to the change. So delta t times this whole thing up here. And you'll notice this is not in the form. Maybe I'll call this matrix, I think we called it like B times omega. P times omega. There's no way to put this in the form. xk plus 1 equals a times xk. What we would need over here is something that multiplies yaw, pitch, and roll, and we don't have that. Yeah, because inside B depends on, this B matrix depends on yaw, pitch, and roll. So in some sense, it depends on that x variable. And then it's multiplying omega, not x, not yaw, pitch, and roll. So we can't use it. Fortunately, we know other ways to represent the attitude other than the Euler angles. What's one that we've talked about? Yeah, Quaternions or Euler parameters. Let's try those. And we can go from yaw, pitch, and roll to Quaternions. Going from yaw, pitch, and roll to the 4 Euler parameters is here. Yaw, pitch, roll, 2, beta naught, beta 1, beta 2, beta 3. Be given that way. So if we use the Euler parameters as the state, I'll just write EP as the state. Okay, x equals beta naught, beta 1, beta 2, beta 3. Well, let's say xk is that time k. Notice our state is now bigger. We've got a state, the dimensions of the state, n is equal to 4, because there's 4 states. One of the forms of the Euler parameter kinematic differential equation, which was in chapter 3 of the book, but maybe we didn't say much about it. So this is actually pretty nice because we've got the rates of change of the Euler parameters is some matrix, and I'll call this matrix just B. And notice it doesn't depend on the state. It doesn't depend on the Euler parameters. It depends on the angular velocities, but that's okay. We could keep changing the angular velocities at each time step. The main thing is this matrix doesn't depend on the beta parameter. So this is in a form where we could write things in terms of a matrix A. And let me show you how. So remember, this is a differential equation. We can discretize it and make it into a difference equation, or the thing that we're looking for. So this state at k plus 1 time step is going to be what it is. This is a 0. This is at time k plus something new from this derivative. So we'll say plus delta t, and then I'll just write the B matrix. And what is this again? This is just the beta vector again. Beta naught, beta 1, beta 2, beta 3 at time k. So I could summarize this as, this is the 4x4 identity matrix plus delta t b, which is also a matrix. And this is all multiplying the state at time k. So this is our A matrix now. So this is in the form x k plus 1 equals A x k. And so this is one of the reasons that Euler parameters or Quaternions get used a lot in industry, is because it fits nicely into a Kalman filter framework. Even though we'd like to think in terms of yaw, pitch, and roll, the mathematical properties of these Euler parameters are just have some benefits that help things out. So, okay, so we can use Euler parameters in the Kalman filter. And we're going to view the Kalman filter as everything's about the Euler parameters now. So z, k, the measurement, equals h, x, k, but we'll use for h the 4x4 identity. We're using all of the Euler parameters. For the noise covariance, this would be something where if you don't know, it's just trial and error. In this case, Q is 0.0001, again, times the 4x4 identity. So some kind of small noise in the process error and larger noise in the measurement error. I'm keeping it the same in each of the entries. So it's going to be 10 times 4x4 identity. The initial state and error covariance. The initial state, if I have yaw, pitch, and roll starting at 0, This implies that my initial state, I write it this way, it's the input for the first prediction step. 0, 0, 0 means no rotation. And in terms of quaternions or Euler parameters, that means beta naught is 1 and everything else is 0. So we're saying we're starting at 2 frames are aligned. And for the initial error covariance, I don't know. I'll just say it's 1 in each of the directions. So it'll be the identity matrix. You could put a 10 in front of that. I don't think it really matters because the algorithm will quickly get to a better estimate. Often R will be given you by a sensor. But this other thing, it just has to do with the actual process. So this is assuming that in the process, comes over here, plus WK, that noise is very small. So we're just saying noise is small, right? Just like over here, there's a plus VK, and we're saying that's larger because it's a measurement. If you take a more advanced class that deals with Kalman filters, they'll give you some more systematic way to find these out, some metrics. We'll go to the MATLAB and see what the magic MATLAB tells us. So just to remind you, this is what we got from integrating, which I'm going to be using some code that was provided by the book from Schaub and Junkins. So that's why I do this add path MATLAB. And in here, I've got MATLAB and it's got all those zillion things from Schaub and Junkins. This is just sort of writing that A matrix, which I had before. Remember this thing, MATLAB writes the 4x4 identity as I4. This is dt times that B matrix, which is 1/2 times this thing with all the angular velocity components. We're starting with psi, theta, and phi all 0. This is just saying from this psi, theta, and phi, spitting out the Euler parameters. And then the Euler parameters are put through this Euler Kalman. So we've constructed the A matrix and we're passing it along, and that Z, we're passing that along. Z is the Euler parameters that come from this set of yaw, pitch, and roll. Can I open that? I go here. Euler Kalman. So because this is already given A, in here we're just defining H, Q, and R, also the initial X and P during the first run. This commenting out is just a result of me doing trial and error and stuff. So this is H, remember to the 4x4 identity. Q is 0.0001 times 4x4 identity. R is that, and then everything else is that. And then this is, again, just the Kalman filter algorithm, all from before. What this spits out is it's taking in the Euler parameters, but I want it to spit out yaw, pitch, and roll. So it's spitting out yaw, pitch, and roll. So let's just see what this does. Hold on. There's the figure plotting part there. All right, it's not looking any better than integrating. I'd like to compare it. They're looking about the same. If I could overlay them, you could see that they are very close. So we're still getting drift. So the Kalman filter didn't save us from that. If anything, I don't know if you noticed, but the Kalman filter was a lot faster. So it seems to be doing a very fast job of integrating, and it's getting basically the same answers, but it isn't right. So I said that there were 2 sensors. There was the gyro, and we'll need to use something like the static attitude determination where there's some direction that we know. Gravity is a direction that we know. So gravity will be pointing, at least when we're near here, will be pointing down. So if we could use the information of, okay, we know where gravity is, we could use that in conjunction with the gyro to get the best estimate. So this is the idea of data fusion. You fuse different data sources, and that's where the Kalman filter can be really flexible because you can put data in different places. So let's do that. Let me first tell you how the accelerometer gives us attitude data based on where gravity is. Let me switch back to here. But maybe to say what happened, we tried this in MATLAB and there was no difference, or very little difference from integrating. except we might say that the Kalman filter was much faster. Let's do some sensor fusion. It means use different sensors to combine to get a best estimate. So remember, an IMU, inertial measurement unit like this, will often also have an accelerometer, just as all your phones and tablets do. And what does it do? You can do some attitude determination, not all, but some attitude determination with an accelerometer. So if the accelerometer is located at the center of mass of a body, it gives this. This is what it measures. It measures something it calls F, but it's an acceleration, and it's equal to the total inertial acceleration of the body minus gravity. So this is just gravity, inertial acceleration of the body. And all of this is being measured, because all this knows about is the body fixed frame. So this is all just being measured in the frame of the sensor, or if you have the sensor rigidly attached to your body, frame of the body. So we could put brackets around these, right? Sub B. Everything is in the body fixed frame. This is the output of an accelerometer, which are often very noisy. And I said that you could use an accelerometer and try to figure out the position and velocity. Good luck. That's why we have GPS. GPS gives you position. If you could do everything with accelerometers, then GPS would be out of business. So what are we going to do here? We're going to assume something. We're going to assume, just to do this example, you need other sensors if this isn't true. We're going to assume that the inertial acceleration of our body is 0. So first we'll assume that this is located at the center of mass and that this thing isn't moving. It's not doing anything, which maybe isn't the best. So we're going to assume that this inertial acceleration is about 0. Body is not accelerating. If we do that, then F in the body fixed frame is just equal to negative of the gravity in the body fixed frame. And remember the usual convention. If we're doing yaw, pitch, and roll, the Z direction of the body is typically down, and we're comparing with an inertial frame where that Z direction or the N3 direction is exactly down. So gravity is acting in this N3 direction. So G as a vector is G in the N3 direction, which is pointed down. This was what, N1, and this is N2, then N3 is down. And we want to write N3 in the body fixed frame, the BN matrix, but now write it in terms of yaw, pitch, and roll. It is this giant thing with sines and cosines. But this is equal to N1 written in the B frame as a column, N2 written in the B frame as a column, and N3 written in the B frame as a column. So this right here tells us what N3 is. So N3 is negative sine theta, the pitch, cosine theta, sine phi, cosine theta, cosine phi. All right, and what about from up here? Got that. So F1, F2, F3 is equal to G times negative N3 sine theta, negative cosine theta, sine phi, negative cosine theta, cosine phi. So based on our assumptions, this is the relationship between, on the right-hand side here, this is the output of the accelerometer. And then we know the acceleration due to gravity. And let's say we're just testing something near the ground. So G is 9.8 meters per second. And then we've got this thing that's a function of pitch and roll. So an accelerometer can help you determine pitch and roll. solve for pitch and roll. Pitch is the easier one. Pitch is inverse sine of F1 over G. And then if we have that, roll is inverse sine negative F2 over G cosine theta. This is good for our phones and things. Like this thing knows its tilt. And so if I tilt it, it knows where gravity is and it reorients. Because all it needs is an accelerometer, which even though this thing is super thin, there's an accelerometer doing its job. You don't usually need your phone or your tablet to accurately get something like yaw. So you'll notice yaw is missing. You can't with just gravity unambiguously determine what yaw is. So you would need to know something else, like maybe the magnetic field direction, which this thing happens to have that too. That's a different problem. So how are we going to fuse this in? We'll use the gyroscope. We'll kind of use the Kalman filter that we've set up, but we're going to incorporate at each moment in time accelerometer data, which will give us these estimates of pitch and roll. So this is where the data fusion comes in. So we'll use the accelerometer. That'll give us a little bit of attitude. I guess we'll call it static attitude determination, pitch and roll. And then we'll treat that as a measurement. Remember, there's that measurement step. We'll treat that as a measurement that goes into the Kalman filter. And in the Kalman filter, like we've already done, that's where we'll use the gyroscope. So the gyroscope will still be there. And then this will give us the best estimate of the attitude. And then you keep repeating that process. So these formulas here will help keep us on track. And it's only as good as our assumptions of, is this thing actually staying still, not accelerating? There's probably a lot here, but are there questions before we do the final MATLAB demo and see what comes out of it? Let's try this out. Data fusion sounds like it'd be something super complicated, but it just means using data from different sensors and different parts of the algorithm. So in this thing, test Euler Kalman, I actually had already coded up whether or not I would ignore gravity or not. So before I ignored gravity, now I'm not going to ignore gravity. So the only difference is, because I'm not ignoring gravity, I'm getting the F1 and F2 from the accelerometer. And then from that, I'm doing those calculations, inverse sine and inverse cosine, to estimate phi and theta. So now that phi and theta is being transformed into an Euler parameter and put into the Kalman filter. So really, it's this step right here that's adding a piece of data along with the gyro, and we could see what happens here. Hoping for the best. And this is what we get. So forget about yaw for the moment, but the roll and the pitch are being estimated pretty well because the accelerometer gives us roll and pitch estimated from the accelerometer, and then the gyroscope is telling us other things about how this is changing. And notice it's pretty good. It's actually pretty good, close to the actual. If I bring up the actual again, it's definitely better than this with all that drift and stuff. But this was supposed to be the true pitch and roll. This is roll up here, and so you'll notice it matches pretty well. So the Kalman filter, including both pieces of information. If I just did the accelerometer, I wouldn't get this. If I just did the gyro, I wouldn't get this. I had to use the two. There's a question related to this? Yeah, go ahead. We're only using the accelerometer as basically a gravity detector. So it's giving us some kind of ground truth about what pitch and roll should be, because we know where gravity is in the inertial frame. There's these different directions. You know them both in your body fixed frame and in the inertial frame. So that static attitude determination isn't useless. You would actually use it maybe along with the gyroscope to get the best estimate in a real space vehicle scenario, depending on where your career goes. As you gain experience, the idea of how do you fuse different sensors to get a best estimate if they're all helping measure the same thing. You'll get better at that. That's kind of it for the Kalman filter part. When we meet again, we're going to talk about rigid body dynamics. All right. So that's it.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series. There are links and other materials in the description.